Okay, so Muddy's point due this weekend. Algorithm choice assignment, group assignment with your groups, your pairs. So only one in the pair has to upload that. Just looking for either the name of one of the candidate algorithms I have in that large document, or if you have another idea that you think would be relevant to the topics of this class, give me a name of that and a couple sentence justification, and that's all I need there. Mini project 4 for unit 4 due Sunday. And the concept check for this unit, I bumped out one more week, so it's actually due next Sunday. So the only thing due this weekend are Buddy's point, the mini project, and the algorithm choice assignment. Any questions? Yep.
If we choose one from the list, do we have to provide justification or just?
No, just tell me on the list, because in the next deliverable, which is a week or two or something after this one, that's when you'll actually describe the algorithm and what you're planning on doing. The ones on the list I've sort of pre-vetted and saying, yeah, I think these are nature inspired. So it should be pretty low, and you're not committing to this. And so it's just showing me that you've thought a little bit about it. You have a backstop, so you can change as well. So should be a pretty low stress assignment. Yeah.
So what type of question do we is the final project more about exploring the algorithm or the more about exploring a question with the algorithm?
Yeah, so it's like you're writing a little white paper that is applying the algorithm in a sophisticated way that will hopefully showcase what the algorithm can do in a benchmark that goes beyond sort of a toy example that I might do in class. So a lot of people, I have a lot of students who either as part of their master's theses or their PhD work, when they take this class, they might say, I have a data set. It's a very large data set on, it's a bioinformatics data set that cell types, and we're trying to classify certain things. And so maybe I'd like to, I've never heard of a self-organized map. But that seems pretty interesting. Maybe it's a way of sort of, in an unsupervised way, clustering all these cells that I'm getting out of this thing. So I'm going to give that a shot and see how well it does. And then I can then scrutinize it. Like if I give you some sort of sample cost functions, I can kind of cook those up to say like, okay, so I know the genetic algorithm is going to work really well here. But if you take one of these algorithms that we haven't described in class, you can kind of put them through the ringer on a more interesting problem. And sometimes, hopefully, it could be something that potentially could lead you to somewhere productive in your own research or work efforts. So, I've had robotics and automation students who were doing robotic design problems using, various simulation platforms that are out there that are often used for, say, reinforcement learning. And they decided to try, I'm trying to build, I have a model of my lab's upright walking robot, and I'm experimenting with new gait patterns. So I'm going to search through the gait patterns, maybe using this alternative approach, and see if it does any better at finding gaits that we haven't discovered for this robot or something like that. And maybe that's something they could end up submitting somewhere, maybe not, but now maybe it just becomes a benchmark for what they're doing in their normal work with a reinforcement learning approach or something like that. So I'm just looking for something that is mutually interesting. It gives me an opportunity to see you show that you're able to synthesize from one of these algorithms and make it work. And also hopefully gives you an opportunity to find a problem that you think is interesting enough to apply these things.
So for the algorithm, obviously the question is interesting, so we can use off-the-shelf algorithm that play around with those?
So the algorithm you choose, I want you to implement the salient features of that algorithm yourself to show that you were able to take a description of an algorithm and build a version of it. But that algorithm may itself, like let's say you do want to use an off-the-shelf optimization test function. Well, if it's a complex, ugly test function, it's fine using a library to implement that. Let's say you are doing some computer vision application, and the point of your algorithm is not to actually do the background subtraction or whatever. Like there are computer vision fundamentals which that you're gonna use off the shelf anyway. Those you don't have to re-implement. Those you can just take APIs, take libraries off the shelf and use those. So I'm not looking for you to do everything from scratch, but I want you to demonstrate that given a description like we've been talking about, like if I could walk into a room and give a very high level description of a genetic algorithm, population of solutions, they compete in this way, they're through differential fitness, it changes the shape of how many are around. You could take that sort of description and you could say, all right, I'm gonna try to build that. And but the things like how you're assessing fitness, how you're simulating, how you're visualizing, all of those things are things that you can take tools that already exist. Any other questions? All right, so moving on in this unit. So we're motivated by simulated annealing. We're gonna conclude there. We'll sort of get really close to that at the end of this lecture, and then we'll conclude it next time, simulated annealing and parallel tempering. But today we're gonna sort of pick up from where we left off last time with these maximal entropy discussion, and then moving on to saying, what is a good distribution what is the maximal entropy distribution that we want to use in our annealer, and how do we actually sample from it? Okay, so last time we introduced the formal definition of entropy, or our version of entropy, Shannon entropy, which is identical to the entropy that you have in physics, but it's off by a constant. So if you multiply this by basically the Boltzmann constant times natural log of 2, then you get the Boltzmann entropy, or for the continuous case, the Gibbs entropy. So Shannon entropy is the average number of bits that an optimal encoding would need to identify each microstate in a macrostate uniquely. So what we're saying by that is if you have a description of a macrostate and it has lots and lots of microstates that could be in it, then you can say, well, how often do those microstates occur? The ones that occur more often, you can assign fewer bits to them. The ones that occur less often, you can give them more bits. And if you use the right encoding scheme, then what that allows you to do is optimize the average number of bits you have to use to communicate with someone, because all of the really often microstates you can communicate with, they happen really often, and you don't use that much information in order to communicate that that's what happened. But then the rare ones, those rare ones are the ones where you need lots and lots of bits. And this is, like the kind of 20 questions game, is that if someone gives you a 20 questions problem and they happen to be someone who always chooses easy ones, then you can always, win, can always, get it done in 3 questions. Whereas you talk to somebody else, they come up with more obscure items that it takes you the full 20 questions in order to figure out what they're talking about. Well, that's exactly the type of optimal encoding. And so the macro state there is kind of the game, and the micro state are the things that the game describes. And so with that, entropy is describing that average information content of that macro state. So this entropy is always not negative. It's always a positive or 0 number of bits. It is bounded above by the log 2 of the number of microstates. So you kind of imagine that the maximal entropy distribution, if you have a continuous distribution, if you could then say, let's flatten everything out, if that is amenable to your constraints, just to say everything that could possibly happen could happen equally, then that will be the maximum entropy distribution, and that will have the entropy of the logarithm of the number of states. And that goes back to what we said, really that's all entropy is it is a logarithmic scaling of a count. It's just how many microstates are in this macro state, and this generalization allows them to occur with different probabilities. So that's the bounded above. So that's the highest entropy for that number of microstates. Sometimes people like to talk about the perplexity. It's kind of funny now, all these large language models like Claude, from Anthropic. Well, Claude, I think they chose Claude because Claude Shannon, Claude is the first name of the guy who outlined Shannon entropy. But then, a competitor, kind of a hybrid model, Perplexity, so that, they use Perplexity. Everybody's just loves information. They're all, congealing around information. And Perplexity is just, if you take the entropy and you raise it to if you basically undo the logarithm, then that is going to give you the equivalent number of microstates. So it could be exponential, it could be 2 to the, but the idea here is, again, sort of imagining that if this was a uniform distribution, how many states would it have? So it's a non-uniform distribution, so it has less entropy than the uniform distribution. So you could say an equivalent thing to say was, well, if it was a uniform distribution, it would have less states than are possible. How many states are kind of possible with that? And we'll see this in kind of some of the examples. But some people have an easier time thinking about perplexity than entropy, but they're just, they just sort of undo the transformation. So you're just getting back to the number of microstates. All right, so that's the discrete form. So this is a useful quantity, and sometimes the thing that happens inside here that you're taking the expectation of is called the surprisal, or the surprise, and so the entropy itself is the expected surprise. All right, so that's our discrete entropy, and then the continuous entropy, I didn't mention this last time, but formally it's actually called differential entropy. It works a little bit different. We use a lowercase h for it. It's the same basic idea. So it has basically the same format here, but with this probability density function instead. This is interpreted, so discrete entropy is an absolute quantity. It is directly related to the number of microstates in a macrostate, and it's just absolute scale. There isn't an absolute scale for continuous differential entropy. Everything has to be kind of related to another unit. And in this case, the core unit is the uniform distribution between 0 and 1. We use that as our core unit of entropy in continuous models. And what this calculates is the number of extra bits relative to the amount of entropy in this distribution. So if this distribution, any random number generator, you go into Excel, you type equals rand or whatever, and it spits out a number between 0 and 1. This is our core currency of entropy, is this thing here. When you ask for any random number out of a computer, it starts out as one of these and then gets transformed into the distribution that you want. This is the thing that you have to build first before you build everything else. And likewise, differential entropy, it has a similar formula as this, has this nice interpretation that it's the number of extra bits relative to that. So if you take the differential entropy of the uniform, what differential entropy do you think you'll get? What value do you think you'll get if I take little h of this thing? 0, that's right. So differential entropy can be 0, it can be negative. If you take the differential entropy of of the distribution, the uniform distribution from 0 to 0.5, this is more compact, it's more ordered, so you actually get a negative differential entropy out of that. So that's differential entropy, it can be negative, its perplexity is the same format, but it has a nice interpretation where instead of being the number of microstates for an equivalent entropy uniform distribution, it is the length of a uniform interval with equivalent entropy. So the perplexity of U01, the perplexity of this guy, is 1 because it has a length of 1. The perplexity of U0 to 0.5 is 0.5. So it's if you were to consider a uniform distribution with the same entropy, how long would that uniform distribution be? That's kind of in a continuous equivalent of number of microstates. And that's where you get that. So those are our two concepts. Once you have these formulas, that allows us to solve for maximal entropy distributions given constraints. Any questions about that? These concepts here, these quantifying these concepts. Yeah.
You would find like f of x in this case, or like.
Well, if you're just calculating entropy, then you have it already. So it would be like I might want to know the entropy of. I might sample a. I might want to know like what's the mixture of majors. Like I want to say like, well, I see that across engineering, there's more of this type of engineer and this type of engineer, whatever. And I get some distribution of that. Well, then that distribution that becomes. In that case, it's discrete, so it becomes the P's that you use up here, and then I can study the entropy of that. If I have a high entropy distribution across majors, then that means that every major has roughly the same number of people enrolled in it. But if I have a low entropy distribution across majors, then that means that there's really one major which everyone's enrolling in, and the other majors are kind of just hanging on. So if you got rid of the other majors, you wouldn't really even notice it because really the school is defined by that one major, not all these other hanger-on majors. So I can get that from data. Likewise for this distribution down here, the continuous distribution, I can get that from, I can say, well, I have a uniform distribution, or I know something about the physical properties of the system, and so I know that a certain continuous quantity happens to be distributed in a particular way, and so I can study the entropy of that distribution. In the max-end case, then, and that goes to this next slide, once I have those things, this is identical to the slide that I showed last time, and I just put it up here to repeat this thing down here, is that I can say maximize big H or little h, subject to constraints. And so there are some core constraints on the distribution. So in the case of a discrete probability mass function, they all got to add up to 1 and they all got to be non-negative. If this were a probability density function, they don't have to add up to 1, but the integral underneath that has to be equal to 1. And they all have to be non-negative. So, and then you add in these additional constraints, and it's outside of the scope of this class, but if you're using for solving for the continuous distribution, there is something called calculus of variations, which is a little bit like calculus over functions, and it allows you to set up an optimization problem, not over numbers, but over functions, and solve for the function that maximizes an optimization objective. In this discrete case, we can just use this method of Lagrange multipliers, which is a way of taking an optimization problem like this one and bolting onto that optimization problem these little penalties that correspond to violating these constraints. And if you bolt them on in the right way and solve that augmented optimization problem, it will give you an output that maximizes this that will meet all of these constraints. And so there just are methods for that, and then that will spit out the P and the F for you based on the constraints. So you either have the distribution already and calculate the entropy, or you have the constraints and maximize the entropy and get the distribution.
Are there like two max-end distributions, like, or they're equivalent?
Yeah, there absolutely could be. I mean, you can have distributions that both have the same entropy. So as an example, U 0.5 and U 0.51. So these two uniform distributions are the same length, so they have the same entropy. But question would be, can you form a problem where both of these meet your constraints and the full unit interval does not? So theoretically, it's possible that it doesn't have a unique solution, but I think it's probably, in most cases, hard to find that, because it's usually if there's enough room for two, then there's probably enough room for something that has slightly higher. I mean, this is hand wavy. I can't say this for sure. For all I know, there's actually some formula that I was forgetting from back in, my own grad level information theory course that says that actually when you maximize entropy, there's this rule that says that they're unique. But just off the cuff, I'd have to say, yeah, I mean, you could have more than one, but as long as you get one that reaches the max, then it's basically equivalent to others. So, but I would be surprised if you could manage to structure this problem so that you get two different distributions that would both have the same entropy and both have max. Yeah, that would just be kind of surprising. Because then I would argue, because in that case, then you'd say, well, which one do you choose? And that becomes an arbitrary choice. And so that doesn't seem right. Like, if you maximize entropy, there should be no room left for you making an arbitrary choice. That's why I really have to think there's probably a theorem that I'm just not remembering that actually says that maximal entropy distributions either, that exist and are unique. All right. So I think any questions about these foundations? Just, we got our entropy. We're not going to talk about differential entropy. I'm just putting it up there that if you do talk about continuous distributions, it's a slightly different framework, but it's the same idea. And we'll actually see some continuous distributions in this discussion. And then max it. All right, and then, so let's see some example max-int distributions. So like when I teach an undergraduate level course in stochastic simulation, I try to build up a vocabulary in my undergrads of which probabilistic models they should expect are good choices under certain situations. And in many of the cases, even though it's a little bit beyond the scope of those classes, behind the scenes, the reason why this situation demands an Erlong distribution, this situation demands an exponential, and this situation demands a normal, comes to entropy, comes to this least biased idea. And so if we start noticing that there are families of constraints, like families of kind of constraint groups, then we'll start noticing, and you start thinking, okay, well, if for this family of problems, I really should probably put in a uniform there if I want to simulate this behavior. Anything else would be adding information that isn't faithful to the current description of the problem. So like, if I wanted to say, what's the position of a particle in a box or line? So let's, so this is, imagine a modeling problem. And this modeling problem says that I have a certain system behavior, there is a degree of freedom in the system, and it is where a position of a particle is in this line. Or, and I'll come back to this a little bit later, let's say you're modeling the atmosphere, and this will be a different solution because it will be a different constraint, but it's the same sort of idea. I need to know where most of the air is. Is it near the ground? Is it in the sky? Those sorts of things. So knowing the position of molecules along a line can be very useful to me when I'm building models. So if my model is this simple thing where I don't know where the particle is, but it can't be anywhere to the left of L, or it can't be anywhere to the right of U, lower and upper, then what distribution should I assume on that particle? So as I run my sim, I'm going to draw a random particle, run my sim, then I run another replication of my sim, I'm going to draw a different random particle and do it over and over again and look at the ensemble of solutions that come out of that and which distribution do I draw that out of? Well, if I go through the max-int process, which I'm not going to do manually here, but if you go through that, then you find the max-int distribution for this constraint is the uniform distribution between the lower and the upper, which maybe doesn't seem that surprising. So there are other ways you could build this. I could choose a beta distribution that is scaled the right way or whatever. I could choose a normal distribution and then truncate it so that it doesn't go any lower than L or any higher than U. And all these might seem like good choices up front, but those have less information in their microstates than this one does. Which means you could say, well, what happened to the information? That information was removed when you made the choice of using a different distribution than this one. And so that means you're actually over constraining the system. And the extra information lost represents the amount of information you added by adding your own constraints. And you want to reduce your constraints because the only thing your stakeholder or the problem description told you was this. So that's why you should choose this one. All right, does that make sense? That's the first one. Just kind of giving some examples here of what some of these maxent distributions look like. All right, so then what will end up being a related problem, what about the space between particles in a box? So in this case, I've got a bunch of particles that happen to be, let's say they're lined up on a line, so we're on a line, and so I can look at their spacing in that box. So a bunch of marbles in a box, and I look down and I say, how are they spaced on this ridge in this box here? And so what's the max distribution of their spacing? Well, what are the constraints for that problem? Well, the constraints for that problem is that all the spacings should add up to the length of the box. So the spacing from the edge of the box to the first marble, all the spacings between the marbles, and then the spacing between the last marble and the other edge of the box, all of those spacings have to add up to L, the length of the box. It's like a conserved quantity. That term is going to keep coming up here as well. So another way I can write this is that the average spacing of the particles is going to be equal to the length of the box divided by the number of particles. That's an equivalent statement. You can rewrite this, you just add a 1 over n to this side and a 1 over n to the other side, and it's exactly the same statement. So either one of those statements, the average is fixed or the total is fixed, end up giving me the same outcome. And what that outcome is that the max int distribution for the distances happens to be an exponential with an average of the average. So, so that exponential, if you were to plot it, it looks like an exponential distribution, and I'm going to, see a sim of this in just a second. But this here, this exponential, it might seem like, okay, yeah, an exponential seems like a reasonable way to draw those distances. It's not just reasonable, it's the least biased way to draw those distances. Okay, and with my other little note here, so if you want to verify this, you can build a little sim where you draw n-1 uniform random variates, that for the box. You sort them, so that's you're basically drawing marbles, you're placing them in random positions in the box, and then you're looking at their distances. And if you plot the histogram of their distances, that uniformly spread set of marbles will have exponential differences between them. And I can show you this. So I've got a little demo here. So I built this little beta distribution explorer. Beta distributions are a distribution that has a support on 0 to 1, like a uniform distribution. They have 2 parameters, alpha and beta. You can think of the beta distribution as if I have a coin in my hand, I don't know if that coin is fair or not. There's a certain probability that it is going to come up heads or tails, and if it's 50%, it's fair. And so based on how I flip that coin, I can change my model of whether I think it's fair or not. And the beta distribution is a distribution of my knowledge about its fairness. And so alpha and beta, these 2 parameters, are what they're called pseudo counts. So alpha is 1 plus the number of observed heads, and beta is 1 plus the number of observed tails. So when alpha is equal to 1, so I can't point with this anymore, when alpha is equal to 1 and when beta is equal to 1, that's your prior knowledge about the coin. So those are referred to as like virtual counts. So it's like, imagine if you're just assuming that there was 1 head and 1 tail in the history. And so that is your prior information. That's your prior expectation. You can have other priors, but you often assume that's the prior there. Well, if you look at a beta distribution, where alpha is equal to 1 and beta is equal to 1. So we assume it's had one head and one tails. Then the distribution, the beta distribution, is the uniform distribution. So, these are my points, my uniformly distributed points up top here. And this is my histogram of their locations, and it is uniform. So I just did that because I can now, let's say I drag my alpha and I make the alpha very large. So now I can make it, I can try to make it 20. All right, we'll just pretend it's 26 because it's easier to think of as count. Now that I've made my alpha 26 and let my beta equal to 1, what I'm saying is I've seen 25 heads and 0 tails. So what do you think happened to the distribution of my knowledge about the probability, about the fairness of this coin? Does it seem like it's a coin that's biased one way or the other? Which way is it biased? So I've seen 25 heads and 0 tails. Then that would mean that this is my guess as to what the bias of that coin is that it's somewhere in this range. So that means that it could be a completely unfair coin that's always heads, or there's some probability it might occasionally produce a tails, but it's mostly heads. So that's where we get these beta distributions. We can change the alpha and beta, and they just change. This is the kind of distribution on probabilities. So it's weird to have a distribution of a probability, but it's the proportion of heads and tails, it's the fairness of the coin, and this is how I'm modeling the fairness of the coin. I brought that up because notice that if I draw points from this distribution, still between 0 and 1, they're all on one side of the box. And now what I've got down here is the spacing. And so this dashed green line, that is an exponential. And what we see here is that the spacing does not look very exponential. It's got a lot of gap between it and the exponential. And so, so that's the reason why I've got this beta distribution that allows me to play with these. If I move this back to uniform, so I've got a little quick thing there, and I go and there's my uniform distribution, and look at that, the spacings lie right on the exponential. So I like this example because it shows that one maximal entropy distribution, so the distribution of where points fall in the box, is consistent with another maximal entropy distribution of the same system. So just like the maximal entropy distribution would suggest that the marbles would fall uniformly across the box, the distance between the marbles also is consistent with a maximal entropy least bias, which has to be the case, right? It wouldn't make any sense to say that the spacing between the marbles needs a different distribution to be least biased. So these two things go together. This is, by the way, this will end up being for things like Poisson processes that you may have used in queuing classes and so on, is that you've got exponential time between arrivals. But then if you look at who arrived in any interval of time, it's uniformly distributed. And that's exactly this as well. All right, so hopefully that provides a little bit, and I can show that if I switch this the other way, so maybe now I've got beta, it's sort of unfair in the other direction, most of the points are over there, and again, distribution is off. So there's a bunch of things I can shoot this up this way, so it's more hump-shaped in the middle, and we look here. Again, it doesn't match the exponential. So it's that uniform distribution. It's got that exponential spacing. They just go together. All right, any questions about that little demo? Okay. So that's all I'm saying here. That demo was trying to show these two things. Not show them, but demonstrate that when you've got a uniform, you also automatically have the exponential. Okay, so I mentioned the Poisson process. So if my constraint is that I've got inter-arrival times, so people are arriving in a store, and I can look at what time they arrived in the store, and then I can subtract those and say, what's the time in between people arriving in the store? Well, that's a time, so it has to be non-negative. And I know from my data that there's a mean inter-arrival time. Now, a lot of times you go to a stakeholder and you're trying to optimize their process. And you might just want to know, well, how often do customers come? I need to be able to prepare for that. Or you're designing a network, you're designing a load balancing setup for some IT situation. And you need to sort of know what's the traffic like? How often do people come to the website? And the only stats they may be able to tell you was we get on average 5 visitors a minute. That's all they've got given you. That's only information. Now, you don't know what that distribution looks like. Hopefully they've got actually the inter-arrival times. You can look at a histogram, you can see if it's, hopefully they've got all that. If they don't tell you anything more than the average, and just by the constraints of the system, it has to be non-negative, then your best guess at the distribution is the max int distribution. And if you take this here and you solve the max int, it turns out that that is nearly identical to what we did down here. So we've sort of already solved this problem, but this is over in the continuous case. And this is saying that even in the continuous case, under these constraints where you fix the mean and you're non-negative, then the max int distribution is exponential. And so the Poisson process, if you're familiar with this concept from, again, often comes up in queuing classes, there's network classes talking about the Poisson process. This is the least biased model of arrivals or locations given a mean and no other info. So I say locations. In weather forecasting, for example, you have to forecast where rain's going to fall. And they use a so-called Poisson point process. So it's a Poisson process not over time, but over space. And the spacings between rainfall events are exponentially distributed for the same reason. That's the max int distribution. If you have no other, all you know is that there's this density of rain events in the area. So on average, every 2 miles you get a rain event. Then you'd say, well, then where, if I need to simulate the rain events in a weather model, then where do I put that? Well, you can use a Poisson point process in space, and that comes from, it's the max entropy distribution given the single constraint of average. Questions about that? Make sense? So exponential, this thing, it's not arbitrary. It actually comes from the types of math that we've been talking about. Now, what about if your stakeholder comes to you and they say, this is a process that may not be non-negative, it's possibly negative, or it's the mean is so large and the variance is so small that we basically assume it's practically that the negatives technically, like we're okay modeling them with a distribution that can produce negatives because the variance is going to be so small that that's going to happen so rarely that it's effectively like it's not producing negatives. And so we're just not going to worry about the constraint that X has to be positive or non-negative. And so these are the only pieces of information they give us. Up top, they gave us mean and non-negative. Down below, they gave us mean and variance. What do you think, just based on your history as being a quantitative person, and sitting through these classes and seeing these types of models, what do you think likely is the best distribution in terms of max int for this case? What do you see over and over again? When people give you a mean and a standard deviation or a mean and a variance, what are they usually talking about? What do they usually couple that with? What is the assumption? What type of distribution do we normally assume? This could be any distribution, right? Every distribution has means and variances. In an exponential, they're coupled. You can't separately set the variance and the mean, but most distribution, you can separately set the mean and variance. So you can choose pretty much any distribution if somebody gives you mean and variance, but people don't. What's the distribution that people typically choose when you give them a mean and a variance? Yeah. The normal distribution. The normal distribution. And that is not just because, I don't know, it's not a mistake. You solve the max int on that constraint, you get the normal distribution out. So that is the least biased distribution for the assumption that you have to fix the mean and fix the variance. Yep.
Going back to the previous question, what would be like the constraints on the, that would yield the exponential for? Like,
The constraints, the constraint is the mean spacing.
oh, sorry, the one on this.
So the constraint here is that all the spacings add up to the total box length, which this here, if you just put a 1/n, the number of particles on both sides, it's equivalent, and then you get the constraint that the mean distance between them is fixed. So whenever you see mean is fixed or total is fixed, those are what I fit into the conserved quantity space. So like people ask me how to model things all the time, and they say, look, which distribution should I use or whatever, and I ask them for these things, what can you tell me about the variables? And if they say, well, it's an energy process, I'm like, oh, energy is conserved, we're gonna write that down. Anything else you can tell me? And if that's all they tell me, that there's conservation and that there's an implication that the support is always positive or non-negative, then I say, okay, just use an exponential for that. That's because, whenever we see this over and over again, conserved quantity and non-negative, it's always going to come up exponential. That's what the exponential is for. And then, they go farther and they add in this constraint on dispersal. Like, oh, okay, so now I can't just assume the exponential dispersal. I have to fix my dispersal to this here. Then that changes the math. But if that's all they give me, then okay, I'll just use the normal for that. So these are not arbitrary choices. These are information theory inspired choices. Okay, and so the central limit theorem, you remember that? Anybody remember the central limit theorem? They could state it. So central limit theorem tells me that if you pull up these carpet squares, if there's a mat under here, and I think there usually are mats and American carpet sort of sets up here, then you would find a bell-shaped wear pattern. It would say that if you looked really closely at these handles of these doors, you would find a bell-shaped wear pattern. The central limit theorem says that if you add up a bunch of independent random variables, the sum over time, as you add more and more of them, will become normally distributed. And that, I hope, now that we start talking about entropy, should start feeling right. Because, somebody, let's say they go and the first person to ever open one of these doors, they push on it one side of it, they push really hard, and they wear a little bit of a smudge off the paint or something like that. And then you can tell, Ted always destroys these doors and he goes through them. So I could tell that he's been there. So not only do I know it's a door, but it's a door that's been used by me because I can tell the wear pattern is unique to me. But they say, but don't worry about it. It's kind of like, what the barbers always say, what's the difference between a good haircut and a bad haircut? 3 days. So it's that same sort of idea, that over time, more people are going to use that door. And as they use that door, then that wear is going to blend together. And information about the history of the wear is going to disappear. So then we can say, well, then what is the equilibrium distribution of wear underneath this carpet or on that door? And that distribution is going to say, well, what do we know about it? Well, the average person pushes on that door handle in the middle, and the door handle's size constrains the variance. So we would know that whatever it converges to, that distribution is going to have a fixed mean and a fixed variance. So what distribution has the least amount of additional information? Because that's what we'd expect over time. And that is the normal distribution. And that is a statement of the central limit theorem. That as you add up independent random variables, the distribution of their sum becomes bell-shaped. It's not an accident, it's the second law, basically. The second law of thermodynamics, acting through probability distributions. Questions about that? Okay. All right, so showed this example from last time. natural language processing, species distribution modeling, as you start getting information like, so I can go back to that because I kind of went through it fast last time. Yeah. So like in natural language, so once upon a time, if you were typing at Google before they now things are very different now. But once upon a time, you do text prediction. You're typing on your phone. It's trying to guess the next word. Well, they know that, okay, so based on the words that you've given me, I'm in a world where the previous word was the. And then so I look at all of the sentences that I have access to. And after the, then, so this is a conditional distribution. Then what comes after? And I can say, well, I found the river. I found a sentence that says that, the forest, the sun. I found sentences like that. The quietly never comes after it. The runs never comes after it. The stone, I found some of those. And I found lots of the rivers. So I'm going to keep adding until I count there. And I found some forests. So you could go through and you build a distribution of, after what things come after it. And then I can break down each one of those words into features. Now, I have to choose those features. So this is actually a place where bias can leak into it. But so I'm saying that, well, of all of these words, some of them are nouns, some of them are verbs, whatever. So I've got their part of speech, I've got their length, some of them are long, some of them are short, some of them are related to nature. So I come up with these features and I just chose these one, nature, word, noun, or long. And then from there, I can come up with a constraint that says that on average, after the word the, then 80%, there's an 80% probability it'll be a noun. And there might be I could come up with probabilities for each one of these categories. And that's kind of what is kind of down here, where it's saying that for nature, there is the corpus, that's my stats. There is a high probability of a nature word, there's a high probability of a noun, there's a low probability of it being long. So it takes these orange bars as the constraints, because you can write those probabilities, which is formulas. So they're just equations, across all the words, across all the probabilities of all of the possible words. Then we want the mean nounness to be whatever comes from the data. And so if we do the maximal entropy distribution across those constraints, it gives us a distribution across words, and that's in the green bar. And that distribution matches my constraints by definition. It's just how the maximum is built there. So, and that distribution is what's up here. So of the small number of words in my dictionary, then after the, it's telling me do not put another the. Do not put a vast, do not put a quietly or runs. If you didn't have either other information, then I would choose whether, river, sun, or stone. But forest might happen there. So then we have to figure out how we get from these probabilities to actually drawing from them. And that's something we're going to get to, but that's how this has been shaped. Does that make sense? How you can take data, form constraints, solve the max-in problem, and it gives you a distribution on possibilities that are consistent with that data, the least biased distribution. And this is one that was really important for NLP because people came up with their own heuristics. Like it's easy to sort of say like, it feels like, these words come after the or whatever. And you're like, I don't want it feels like, how do I make that objective? And this was a way to objectively say, how do I push out all the information and say, what is the most fair distribution across my words based on the words that I've observed. And then you can do the same thing. I'm not going to do that example again, but the same thing with species distribution, 3 features, elevation, temperature, moisture. You can say where you've found them. You can build constraints. So the probabilities of being in any one of these squares. You can define a probability of that this species is at high elevation, and a certain temperature, certain moisture, and then that sets up this distribution. This is the max-it distribution for where to find these species. And then you can use that for looking for those species. So if I plot them in different places, the distributions move around. There you go. Okay, questions about that? This demo. People still use this today, very popular. You can find lots of tools built to help you build these distributions. Okay, so I mentioned conserved quantities. Now we're finally getting back to something that we're going to use in the simulated annealing. So, maximum for conserved quantities. So energy at a given temp. So, or, the energy available for us to perturb a microstate at a given temperature. Well, energy's got to be non-negative. Energy, because I've defined temperature the way it's defined, this heat bath construct, I'm assuming that we're at a thermal equilibrium where we can assume the temperature is constant. That comes with it, the baggage that the average energy available for these microstates is constrained to be proportional to the temperature. So basically the average energy is fixed. Well, we've seen this over and over and over again. So this is telling us that we are going to, the probability of any microstate is going to be proportional to an exponential of its energy. So an exponential distribution over energy. Now they're discrete microstates. So that's sort of the interesting transition here is that I'm not, like if I just cared about energy, this would be an exponential distribution across energy. But I'm actually looking for a distribution over microstates. Microstates are a high dimensional mess, but each microstate has an energy. Its energy must be exponentially distributed. But that mapping of microstate to energy is going to be the thing that actually shapes the microstate distribution. But however I draw my microstates, it must be that the energy of those microstates I draw should be consistent with this proportionality constant up here, where the probability is going to be proportional to the exponential, which comes from this max int distribution over that energy constraint. So how do I get that discrete distribution? Well, I just say, well, what microstates do I care about? So I've got these 6 microstates that I'm trying to decide between here. And so each one of them has an energy. So, okay, 6 microstates, 6 energies, then I know each probability of the 6, what they're proportional to. So in order for me to get a probability distribution, I just need to make sure that all of the probabilities are proportional to this and sum to 1. Well, how do I ensure that? I divide them by a normalization constant. And that is just the sum of everybody's proportionality constants. And so if I take what I'm supposed to be proportional to, and divide by that plus what everybody else is supposed to be proportional to, then I will get probabilities out that are proportional to this and sum to 1. And this thing in the denominator is what physicists call the partition function. And it turns out if you have the partition function, you can do things to it that generate lots of interesting quantities and physical properties and so on and so forth. But most of the time we don't care about it because as we'll see, most of the time we use this, we divide one probability by another. And so the denominators, which are common, cancel out. And so what we usually care about is just this proportionality constant up top, which is called the Boltzmann factor. Now, this, to anyone who's been in machine learning class, should look a little familiar. This is what in machine learning we call softmax. It is what assigns the, if you've got your neural network, it's maybe it's a multi-class neural network where it's trying to say, I've got 6 possible things that this image could be. And so it could be a dog, could be a cat, could be a mouse. It's got 6 different things there. And it says, I have this much evidence for each one of these 6 things. Well, I need to turn those evidences into probabilities that I can use to then draw a prediction on what it actually is. And those, and I'll show this in a demo here in a second, those evidences will relate to these energies. So for us, higher energies are less probable, but for a neural network, higher evidence, higher logit scores are more probable. But so they're just the flip of energy there. And so I know my proportionality. I know that cat should be twice as likely as dog. And then so I normalize, and then this is what gives me a probability. And then that probability is what I draw from to actually make my predictions. And that's the so-called softmax, which I'm going to, again, show you in just a second how this looks graphically. This is where softmax came from. So yeah, let's just go and do that. So a little softmax demo here. All right, so I'll do the energy view first. So up here, I've got these 6 microstates, A through F. And I know that microstate A has a lower energy than microstate B, C, D, and E. And then F is sort of similar to A. And so I would expect then that, so what softmax tells me, or sorry, not what the Boltzmann distribution tells me, that's what this is called, the Boltzmann distribution, or the Boltzmann-Gibbs distribution, is that the probabilities kind of look like the flip of these sliders. So if I were to say all equal there, so if they all have the same energy, then they're all equally probable. If one of them has a much lower energy than all the rest, then that one should be the winner. That one should be super probable, the rest should not be very probable at all. If there's a gradient, then if there's a gradient in an energy, I should get kind of a gradient of probabilities. So that's when we map from energy to probability here. And the way that the temperature does is that, so right now I've set my temperature equal to 1. Now if I change the temperature, so let's do, this is probably a good one. So if I change the temperature, it's going to change the relationship between the energies and the probabilities. If I move the temperature all the way down to the coldest, then this becomes a deterministic choice. So the probability distribution is such that when you draw an answer, you always just take the maximum. So this Boltzmann-Gibbs distribution, when temperature is very cold, is just a maximum. It just chooses the maximum, or in this case, the minimum energy. If I then flip the other way around and I make it very hot, then it doesn't matter the relative energies. Because when it's very hot, I still end up getting a uniform distribution. So this temperature parameter is nice in that it allows me to bias things toward just taking a maximum or kind of allowing more diversity. So there's maximum diversity at high temperature. There is sort of fitness. There's sort of, if we're thinking of it as fitness, there's kind of fitness diversity at high temperature. And I can, down here, I'm actually showing that exponential with these 6 samples of the exponential, and it's doing the same thing. So down here, we get a peak at the highest or lowest energy. Here, they're all uniform. Now, in machine learning, what you do is you replace the E's with negative scores. So you've got these 6 outputs, these 6 neurons. Each one of them represents evidence or logit scores for a particular output. So I'm going to flip this to logit view or score view. And then now what's nice about this is higher scores mean higher probabilities. So these sliders are kind of matched by this probability distribution. So if I play with these sliders, then I get the same things changing in this distribution down here. But then in softmax, you always have this temperature component. And so if I swing my temperature down, then that's just saying that whatever my neural network is, whatever the mode of my neural network's distribution is, I want to use that all the time. That's my prediction. But if I'm not quite sure about that, if I want some flexibility there, then I could go into my softmax function and I can change the temperature to be higher. And it will gradually get more and more uniform, where regardless of what the evidence is, I still end up choosing roughly equally across my options. So that's softmax, and it comes directly from the Boltzmann-Gibbs distribution, which is a mapping of energies or evidence to probabilities. Questions about that? It's the maximal entropy distribution given a temperature. So you set your bias towards diversity, and after you set that temperature, then you have evidence coming in, and you say, given the evidence and given the bias towards diversity, here is the maximal entropy way I should draw my samples. And that's what we just got written out here. All right, so this is what we're going to use in simulated annealing in order to choose how to move from one microstate to another. So we're going to choose how much energy is available to us to make big jumps versus little jumps. But simulated annealing came later than the Boltzmann Gibbs. So what did people originally use the Boltzmann Gibbs for? And is that something that we should just be aware of in our kind of nature-inspired, like, if we're learning about computational methods and other things like that, then where did this come from? So that's what I'm going to go to next. Any questions though about this? Softmax, maxent, are they all linked together? Okay. So before we go there, quick thought experiment. There's an air pressure distribution in the atmosphere. So, let's say we want to model that air pressure distribution. So you know that, you go up high, it's usually less pressure. You come down low, it's usually more pressure. In the ocean, that is a fluid that it's a liquid. It can't be compressed. It's an incompressible fluid. So there, a similar relationship, low pressure, high pressure, really has to do with the fact that when you're down deep in the ocean, you got a lot of water pushing down. That's not what happens in air though, because air is compressible. And so you can shove a lot of air down here and have a lot of less air up there. So then the question is, what is that distribution of air pressure? So we want to use what we've learned from information theory about the constraints of this problem to try to predict what we'd expect logically. What does logic suggest the distribution of pressure in the atmosphere should be? And so what do we know? Well, we're going to assume an altitude range, and these exist, where the temperature is roughly constant. So this model is only going to work for those chunks of altitude. Once you move into a chunk of altitude where the temperature changed, then this isn't going to explain the variation due to the change in temperature, but it can still help us get there. But in a large chunk of altitude, we assume temperature is constant. And also in that chunk of altitude, we assume that the energy of molecules is fixed. So some molecules are energetic, some are not. When those that are energetic bump into others, they trade their energy. And when they trade their energy, then they end up, that trade does make one less energy and the other one higher, but the total amount of energy is conserved. The average energy across all the molecules is the same. So this tells us that the average energy across all molecules is fixed, and because we can hold temperature constant and assume this sort of thermal equilibrium condition, the average energy is equal to KT. So we've seen this before, right? This is what our Boltzmann Gibbs was all about when we were coming up with energy distributions. But now I'm talking about pressure distributions. All right, so what's our outcome space? Thinking like, optimization, what is the decision variable? What is the, and its height. So where are the air molecules? Are they here? Are they here? Are they here? If there are a lot of them down here, we're going to have high pressure. If there's a lot of them here, we're going to have high pressure. So we know that height is greater than or equal to 0. What else do we know? From physics, we have a way to map our outcome space to a fitness function, a landscape, an energy landscape. The potential energy landscape from physics for a molecule of air, a packet of air, is the mass of that packet of air times gravity times height. So we have an energy function. So every height we can associate an energy with, and the average energy is fixed. Follow so far? All right, so then these are our two constraints. The average energy, mgh, is fixed to kT or kdt, and the height is greater or equal to 0. So what do we think is the max nth distribution of height based on all of the examples I've shown you so far? It's an exponential. It's a Boltzmann. If we think about, if we think of our last example where we had microstates going to energy is exponential. And so here we've got height going to energy and the energy is exponential. So it's a Boltzmann distribution across height. All right, so that's pretty cool. So we're saying that the density of height is proportional to this exponential, which takes this form. This again is our Boltzmann. It's exactly our Boltzmann, minus E over KT. This is the so-called barometric formula. This is the formula that explains why your ears pop when you go up a mountain. Now, of course, temperature's changing or whatever, but it's but within certain volumes of air where we can assume that the temperature is roughly constant. This is what makes it so that you get lower pressure up high than down low. It's all due to the gravitational gradient. So the idea here is that the lowest energy state for air to be is right next to the Earth. But there is enough thermal energy that kicks that air up and it allows it to move up higher. But how far does it go up? Well, we model that as an exponential. And so occasionally it gets kicked up really high. And there occasionally are several little packets of air that got kicked up really high. But most of it is down low. And that's what sets up a pressure gradient. And that pressure gradient is distributed as a Boltzmann. I think that's really cool. That, that again, before I learned this, I just always assumed the pressure gradient has something to do with just, there's just a lot of air above me pushing down on me, and that's why there's higher pressure here than up there. But it turns out because air is compressible, that math, which kind of works a little bit more underwater, doesn't quite hold water, for in the air. And so what's actually doing it, it's maximum entropy is doing it. So if that's the only thing we know, these things here, and everything else is just random, and washing away signs of anything, I can try to pull the air down, I can try to push the air up, but I'm going to let go, and randomness is going to take over, and it's going to erase all the information. What's left is that pressure distribution. Does that make sense? And I want to show you another little demo that kind of drives this point home, but in terms of money. So this guy here. So there's a group of, there's a subset of physics called econophysics. So physicists who apply physics to economics. And this is one of their favorite examples. And I like it too. So imagine if all of us in the room, imagine if there were more people in the room and all of us in the room would put on blindfolds or whatever, or just randomly bumped into each other. Every time we bumped into each other, we gave a random portion, or we accepted a random portion of money out of, if we all had money in our wallets. I know it's a little dated example, but let's say Venmo or whatever, you tap your phones together and a random transaction happens that is feasible. So it's based on the amount of money in your account, but you trade a little bit of it to the other person. So sometimes you get money, sometimes you give money. Note that the total amount of wealth in the room never changes. The average amount of wealth in the room across people never changes. But the actual amount of money you have varies over time. So the question is, what's going to happen over time to the distribution of wealth? And before I'd set this up, I primed you with the max end stuff. If a lot of times when I ask students this questions, they're going to say, oh, well, it's going to average out and everybody's going to have the same amount of money in their wallet at the end of the day. But then I think, well, so that right there, that would be this. That would mean everybody's got $10 in their wallet. And if you look at this, does not look like a natural distribution. So you say, well, what is a natural distribution? So this goes back to how we started the unit. Maybe it's uniform. So maybe there's an equal probability that you could have $35 in your wallet as $1 in your wallet. Well, that also, this doesn't look very natural. So what is that? Well, now we know how to do maxent, and I just described something that had a fixed average, and wealth is always positive. So that's the reason why I've got this theoretical exponential here. We would expect that if we just do random exchanges, that's where the money should go. And so let's just do it. Let's run that sim. So I'm going to do 500 agents to make this a little faster and run that sim. And even though they all started out with the same amount of money in their wallet, they converge to the exponential. So, okay, well, maybe it's let's concentrate. Let's say one person has all the money and nobody else has any money. Maybe that'll change. I run that. It slows things down, but it will eventually converge to an exponential. And you could say, well, they all start uniform. Run that, exponential. Bimodal, some poor, some a little less poor, exponential. Starts exponential, stays exponential. So this is the baseline. So when we talk about these Gini indexes and all these, if you go to economics and wealth distributions, this is the null expectation, is that you always are going to have a few number of people who are a lot of money, and most people don't have that much. What becomes interesting is when you go into countries and it's uniform. Well, we know that in nature, you don't get uniformity without putting energy into the system. So you have to spend energy to keep things uniform in nature. And likewise, usually when you have uniform wealth distributions in societies, it's because those societies are constantly investing in redistributing wealth. On the other flip side of that, if you see something that's spiked so that it's under the exponential, so that means that more people than expected are poor, and there are several people that are really, really, really rich, that's also not exponential, which suggests that there's something else in the system which is pulling it away from exponential and redistributing the wealth to a certain set. So by looking at deviations from the exponential, you can start diagnosing what types of processes are in a society that are actively adding energy to the society to actively reshaping. Because once you let that energy go, the null expectation is it goes to an exponential. Questions about that? All right, so basically we're gonna stop here. We're gonna pick up next time with Metropolis sampling. And this will give us the Metropolis Hastings algorithm, which will then give us simulated and that'll be, and then I'll mention parallel tempering, and that will end the unit on this kind of physics inspired stuff. So, all right, don't want to keep you longer. Have a good weekend. If you have any other questions, feel free to bring them up. Otherwise, remember to submit your algorithm choices this week.